So this is the lesson for the weak acid and weak base calculations. I will mention that before we start, we touched upon something that was covered in class, which is very minor. When we take the pH and pOH, so let's say the concentration of H3O plus happens to be 1.5 times 10 to the power of negative 6, right? So the negative log, when you take that, the log of something comes from the first digit here before the decimal point comes from the exponent, right? So this will be it'll be like negative of negative 6 point the log of whatever 1.5 is, which happens to be a positive number. So if you take the negative log of 1.5 times 10 to the power of negative 6, you will get 5.8, because you take negative 6 and then you're adding like some positive small number. So this is, and you take you get negative of negative 5.82, which is positive 5.82. Right, so that's how the logs are done. But the important thing here is in terms of significant figures, right? So the number of significant figure here is 2. This 6 does not count there. So when you calculate the pH, whatever goes in front, anything before the decimal place does not count towards your significant figures because it came from the exponent. The significant figures in a power or pH or pOH or anything will be you only count the number of digits after the decimal place. So this would be 2 significant figures after the decimal place. So this would be a correct solution for the correct number of significant figures in a calculation like that. So that was just a brief intro. Here are some examples of weak acids. Here are some examples of weak bases. And that's all we're going to say about that for now, because we're more interested in how to calculate percent ionization. So we know that, so first of all, when I say Ka and Kb all the way back here, what does that mean? So whenever I have, for example, let's say I start off with an acid. So any weak acid, we'll pick one called formic acid from the next page. So this is a weak acid, so it's going to dissociate to give us HCOO minus plus H3O plus. And when we write our equilibrium expression, we're going to write Kc equals HCOO minus times H3O plus divided by HCOOH. I'm ignoring the water because it's in liquid state. All the others are aqueous, so I will count them for my Kc. We are not going to call this Kc. Instead, we're going to call it Ka, which is the exact same as a Kc expression, except I'm writing it for dissociation of an acid. So whenever you see a Ka, you know that an acid is dissociating. Acid is dissociating in water to give its conjugate base plus some H3O plus ions, right? That's what Ka means. It's the same thing as Kc, and it also signifies the same thing. It signifies the extent of the reaction. So Ka more than 1 means that your products are favored heavily over your reactants. But when we're talking about weak acids and weak bases, we observe that the Ka is lesser than 1. But still, there's 1 times 10 to the power of negative 4 Kas and 1 times 10 to the power of negative 12 Kas. And there is a difference between these two acids. This will be a stronger acid relatively than this one. Both of them are considered weak, weak acids. But this one will give you more H3O plus ions. So this one will move more to the products than this reaction. Right? The negative 4 will move more to the products. So the Ka basically gives you how strong your acid is in solution. If it's greater than 1, it is a strong acid. So that was our list that we went through. If it is lesser than 1, it's considered a weak acid. But even in weak acids, there are varying levels of strength. And similar idea for bases, except instead of in your base, if you take ammonia plus water. Our Kb, B for base expression, is going to be NH4 plus times OH minus divided by NH3. Right, and again, this also gives us the extent of the reaction. Just for acids, there's a new term that we're going to talk about. It's called percent ionization, or P. And this is basically the formula that's on this slide over here. So it's concentration of acid, which is our H3O plus, divided by HA times 100%. So if you think about it, it's very similar to what we did. It has strong relations to our Ka. It's just we're not considering this bit in our reaction. So percentage ionization is H3O plus divided by HCOOH times 100%. So it's very similar to our Ka, and it also gives you the extent of the reaction. It tells you how much acid is ionized, or how much H plus I'm getting. So if this was the Ka, my percent ionization would be higher than this percent ionization, because this had a low Ka, had a low percent ionization. Ka and percent ionization tell you the same information, but they have different numbers because there's this extra term here for Ka. And Ka can be used for a bunch of reactions. Percent ionization usually only applies to acids and bases. So the pH of a 0.1 mole per liter methanoic acid is 2.38. Calculate percent ionization. So we know percent ionization is, so again, you might think about starting with a nice table. It's important to just look and see what you have, look at your formulas, and see what you need to calculate. We know percent ionization is H3O plus divided by methanoic acid is formic acid. It's the same thing as what we did before. And we have concentration of formic acid. We need to know concentration of H3O plus, which is just 10 to the power of negative pH. Right, so I can do that calculation basically in one step. No, why did I mess up? 10 to the power of negative 2.38 divided by 0.1. Okay. Percent ionization is, times 100%. I forgot that. It's kind of important. So the times 100 is 4.17% ionization. So you can see that methanoic acid has a very low percent ionization. So it also helps to contrast this when I say strong acids have 100% ionization. So if I take a strong acid, HCl, 0.1 molar, right, and I try to calculate percent ionization, my H3O plus divided by HCl is 0.1 divided by 0.1 times 100%, which is 100%. So that says that my H3O plus equals my concentration of HCl. So that's what we've been doing all this time. Strong acids have 100 or close to 100% ionization, 99.999. Weak acids have percent ionizations that look like this. And as far as weak acids go, methanoic acid is kind of one of the stronger ones. So it's still very low. So acids are only probably going to get weaker than that. So it's not, yeah, that's that. Well, yeah, that's what we talked about. Ka means an acid, Kb means a base, but it's literally just a K. There's no difference there. And this is looks like the general formula. H3O plus, A minus, HA. This is how we generally represent an acid and its conjugate base. It's something with an extra H plus that it can lose, and once it loses that H plus, we have A minus left over, which is this guy. Yep. Yeah. Oh, important to note that K values will be Ka and Kb values. Both are at the back of the textbook. And, well, we will either give you a copy if you need it, or, well, if you need it, we'll definitely give you a copy. We'll probably include a table at the back of the test or whatever as required. Okay. I don't know if there's a base thingamajig. Oh, there is a base thingamajig, so we'll get to that later. Okay. Determine the Ka when 1 H plus is donated. So we have to determine Ka now. So H2CO3, determining K means we have to have an ice table, but as we'll realize very quickly, these ice tables for acid bases look exactly the same. Like they're very easy to improvise for weak acids and weak bases. They always look the same. I start with some initial concentration here. I have 0, 0. My change is going to be minus x plus x plus x, 0.24 minus x, x, x. And now I'm going to look at back of the textbook, and I'm going to find H2CO3. I cannot find H2CO3. Oh, I found H2CO3. Ka is given to be 4.5 times 10 to the power negative 7. Excellent. I have found my Ka from back of the textbook, and now I'm going to set up my... Oh, I have to determine Ka. Jokes. Don't look at the back of the textbook, guys. I lied. This is what I have to find. Well, it is given in the back of the textbook, but I'm asking you to calculate it physically. Here, I know my x value is 3.49. Right? So, well, not entirely. My x value is not 3.49, but I can calculate my x value from 3.49 because from my pH, I can go to my H3O plus concentration, which is 10 to the power negative 3.49, which is 3.23 times 10 to the power negative 4, which is equal to x. So this is 3.23 times 10 to the power negative 4. X is 3.23 times 10 to the power negative 4. This is equal to 0.239 something something. Right, so 0.24 minus answer is 0.2396. Basically 0.24. There's no difference there. So my Ka, do not look at the back of the textbook, is equal to x squared divided by, 0.24 minus x, which we have found x squared. So we do 3.23 times 10 to the power negative 4 squared divided by 0.2396 gives us a value of 4.35 times 10 to the power negative 7, which is basically what we found at the back of the textbook, plus or minus a little bit, right? So that's how you calculate the Ka, if I ask you to calculate it. Yeah. Okay, so this is better. So this is what we will most likely be actually calculating, the pH of a solution if I give you the Ka. So this was going backwards, which is going the other direction as this question. So ethanoic acid, I'm going to write my formula, ethanoic acid. Was it 0.1? I have to find my pH, which means I have to find H3O+. right? So because they're all linked, right? And therefore I know my Ka. So first thing I'll do actually is I'll do my initial concentration divided by my Ka is greater than 500. Therefore, justified. Cancel out this negative x, make life easy for myself. 1.74 times 10 to the power of negative 5 equals x squared divided by 0.1. I have got rid of the negative x. This will be the general expression after you do an ice table for almost any weak acid or weak base. So the Ka or Kb equals x squared divided by 0.1, and x is your H3O plus if it's an acid, OH minus if it's a base, right? It will always look this way. You can show me an ice table, but if you are confident enough to do the ice table in your head and just straight away write this equation, all power to you. So I'm doing this times 0.1 and taking the square root, the Ka, 1.74 times 10 to the negative 5 times 0.1, and then taking the square root of that answer to give me an x value of 1.32 times 10 to the power of negative 3. From here I can easily calculate my pH by doing negative log of that H3O plus concentration or H plus concentration to give me a 2.87 pH. Right? I'm not too worried about sig figs for the moment, but hopefully you will be worried about them on the test to a reasonable extent. Yeah. Calculate acid ionization constant of acetic acid if a 0.1 mole per liter solution to equilibrium has a percent ionization of 1.3. Okay. So this, I will point out here that if you contrast this with so for the same ice table, if you have to find your percent ionization, which is H3O plus divided by initial concentration of acid, right? Which, if you look at the ice table, is x divided by 0.1, right? So our percent ionization in Ka only differs by a x value, or an H3O plus concentration value. So as long as we can find that, it's very easy to go from one to the other. So I'll do it the long way first. If we have a percent ionization of 1.3%, which is 0.013, yeah, and this is equal to H3O plus divided by initial concentration of acid 0.1. So we get 0.0013, which is 1.3 times 10 to the power of negative 3. And then this is the same as my original question, because I know Ka equals, H3O plus times my conjugate base divided by acid. And you can, you know what, I said I'd do it the long way. Let's draw a nice table. Acetic acid. 0.1 minus x, 0.1 minus x, 0, 0 plus x, plus x, x, x. I have calculated my x to be 1.3 times 10 to the negative 3 because that is the H3O plus. Right, and now I can do, basically what I said here. So instead of conjugate base and just acid, I'm going to write what my conjugate base is and what my acid is. conjugate base. So I do this, and this is 1.3 times 10 to the power negative 3 squared, because they're the same, divided by 0.099. So 1.3 times 10 to the power negative 3 squared divided by 0.99 is 1.69 times 10 to the power negative 5, which is my Ka. Right, so that was the way to do it. I didn't really have to draw this ice table. I knew this starting off. I just have to square this and divide it by my initial concentration. But the ice table was the proper way to do it. So yeah. Okay, so this is our base expression, which is very similar to our acid expression. We have base, which is just a B with a lone pair on it, is going to accept a proton from water to form Hb plus, and leaving water with an OH minus. Kb values are found in appendix. Okay, so yeah, okay, this is good. One more question, we'll wrap this up. Okay, so our equations provided here. Thank you. 0.01, we leave water alone. 0, 0, minus x plus x, 0.01 minus x. I'm instantly right away here going to do initial concentration divided by 1.8 times 10 to the power negative 5 greater than 500, hopefully. Just about greater than 500. Cancel the negative x plus x, so my general expression, x squared divided by 0.01 equals Kb, and the 0.01 is concentration. Again, this looks exactly the same as our acid guy. So we do 1.8 times 10 to the power negative 5 times 0.01, square root that answer, and then we get x equals 4.24 times 10 to the power negative 4. The only difference here is when I go negative log of x, I'm actually doing negative log of OH minus, which is going to give me my POH. Right, so if I take negative log of that, I get 3.37, which is still not the final answer because I always want a pH value. So I do pH equals 14 minus 3.37, which is 10.67 pH. And that is it. Homework will be on the other video. I will see everybody in class.